I can see the slides.
Okay.
All right, so let's go to the second talk in the session. The second speaker is Hayato Arai, who is going to talk about the pseudo-standard entanglement structure cannot be distinguished from a standard entanglement structure. So Hayato, floor is yours.
Thank you for the introduction. I'm Hayato Arai from Nagoya University. This is a joint work with Masashi Hayashi, and the archive number is this. If you want to know about details of this talk, please check it. Okay, first of all, we give the brief story of our study. We explain definitions and details later. This talk is addressed on general probability theories. General probability theories, hereinafter GPTs, is a generalization of the model of quantum theory with state space and measurement space. Then, our interest is characterization of entanglement structure. Entanglement structure is a possible structure of quantum computer system in GPTs. In standard quantum theory, the structure of computer system is uniquely determined by the tensor product. However, in GPTs, the structure is not uniquely determined, even if the local systems are completely equivalent to the standard quantum theory, and even if we impose natural postulate about local structures. In other words, the standard entanglement structure is not trivially determined by natural setting about the probability and natural assumption of local structures. Then, many other models are theoretically consistent with natural postulate. Therefore, it is important problem for foundation quantum theory to derive the standard entanglement structure from possible entanglement structures by additional reasonable postulates. This study clarifies the difficulty of this problem. In our study, we introduce a kind of structure so similar to the standard entanglement structure that it cannot be theoretically denied by verification of maximally entangled states with small error. When such similar entanglement structure satisfies self-duality, we call it shared standard entanglement structure hereinafter PSES. Self-duality is important property of standard quantum theory, and it is related to projectivity of measurement. Then we consider the problem that, is there any example of PSES except for the standard entanglement structure? Our result possibly answer this problem. That is, we show that there are infinite examples of PSES. In contrast to similarity of PSES, we show the difference between shared standard entanglement structure and the standard entanglement structure in terms of performance of state discrimination. So we showed that some of examples of shared standard entanglement structure can discriminate non-orthogonal states perfectly by one-shot measurement. And besides, we investigate a diversity of entanglement structure with group symmetry. And we showed that a kind of global unitary symmetry determines entanglement structure as a standard one uniquely. Roughly speaking, a kind of group symmetric condition denies possibility of such shared structure. Okay, let's start to talk about details. We talk on these outlines. First, as a preliminary, we simply introduce GPTs and entangled structures. Second, we explain our setting and results. Finally, we summarize this talk and give some problems. Okay, first we give a simple and brief introduction to GPTs. GPT is a framework that contains states and measurements. The framework is a generalization of quantum theory. Because of the simplicity and easy understanding for beginners about GPTs, we only explain a restricted class of GPTs. And in order to introduce the restricted class, we start the definition of the model of quantum theory, standard quantum theory. In this talk, we consider finite dimensional Hilbert spaces, and we denote the set of Hermitian matrices and the set of positive symmetric matrices as Th and T plus H respectively. In standard quantum theory, a state is defined as a density matrix, and a measurement is defined as a possible delta value measure. When a state law is measured by a P of MI, then the probability to get an outcome I is obtained by the trace. In this way, And the model of quantum theory is defined by set T plus H. Here we remark that the condition that effects of the P of M are positive semi-definite can be translated to this condition. The trace is positive for any state law. And in terms of probabilistic structure, the important thing of this setting is these two conditions. These two conditions are derived from the definitions of states and measurements, and these two conditions imply that the trace consists of probability distributions. And the essential conditions also hold when we replace the set T plus H with more general set K. This is a definition of a model of GPTs. In contrast to the set T plus H, a model of GPT is defined by a set K called a positive cone. Here we omit the definition of a positive cone. If you do not know the definition of positive cone, please consider a subset of Hermitian matrices consistent with certain probabilistic postulates. And K means K means the set of unnormalized states in the model. So, but the important thing is these two conditions also hold in this setting. Here, the set corresponds to the effect is changed to the dual of K, but the dual of K is defined by this condition, and this condition is the same as that of quantum theory. Okay, this is a definition of the model of GPTs. The GPT is a generalization of the theory defined by a positive cone K. Okay, next we explain entanglement structures. Here we denote entanglement structures ES. ES is a possible structure of the model of the bipartite composition system of quantum subsystems in GPTs. In physical system, we only know the model corresponding to the set of positive semi-definite matrices on the tensor product of sub-Hilbert spaces. Here we call this model the standard entanglement structure, here after the CES. However, in GPTs, entanglement structure is not uniquely determined as the CES, even if we assume local system is completely equal to the model of quantum theory. Some tuples of such fundamental operational postulates derive that entanglement structure K satisfies this inclusion relation. Here, the tensor product is defined as the set of unnormalized separable states, and the dual of the separable states corresponds to the set of entangled witnesses in quantum information theory. In this talk, entanglement structure is defined as a model defined by K with this inclusion relation. There is no known reasonable operational property to characterize the CES from such a range of entanglement structures. Then it is an important problem to derive the CES from entanglement structures by reasonable postulates. In this talk, we show the difficulty of this problem. That is, we show the existence of shared structure of the CES. Okay, next we explain our setting and result. We consider entanglement structure with the following two conditions as shared standard entanglement structures, here after PSES. Strict mathematical definition is given later. Anyway, the first condition is called undistinguishability. This means availability of verification of any maximally entangled state with small errors. Verification of maximally entangled state is important task in quantum physics to guarantee that the system fully contains quantum object. However, an experimental verification with some errors does not guarantee that the prepared state is exactly the same as the target maximally entangled states because of the error. Therefore, this condition holds not only in the set but also in another entanglement structure. And the second condition is self-duality. Self-duality means the state space and the effect space is essentially equivalent. Mathematically, this equality is a positive and it's dual. Self-duality can be regarded as the saturated situation of pre-duality. Pre-duality means the pre-duality means this inclusion relation, and pre-duality corresponds to availability of projective measurements. Hereafter, we discuss the existence of such structure, and we assume the dimension of subsystems are equal because we need to consider maximal entangled states. Okay, we explain the details about the definition of PSES. First, we introduce undistinguishability. Let us consider whether the following task is possible or not. In order to prepare a maximally entangled state, sigma, we prepare a state rho in our model and verify that rho is almost equivalent to sigma with error probability epsilon. In order to success such a task for any maximal entangled state sigma, our model includes near state rho for any given maximal entangled state sigma. This task is successful if there exists such a state rho in the model. In other words, if entangled structure has a state sufficiently near any maximal entangled state, then case success is this task. So there are possibility that another entangled structure satisfies this task. For example, entangled structure with this inclusion relation successes this task because the structure has all standard quantum states. Then we consider this concept mathematically. Such a verification is implemented as hypothesis testing. Because the error probability of hypothesis testing is given by the trace norm, then we define the value d of k, defined as this. Simply speaking, the d of k is such a largest distance between k and the maximal entangled states, like this figure. This value means how small error we can verify to exist maximally entangled state in the structure k. For example, if d of k equal to 0, k contains all maximally entangled states. That means we can verify to prepare all maximally entangled states theoretically without errors. Then we consider the condition d of k less than epsilon. And we call this condition epsilon undistinguishability condition, because this condition implies that we cannot deny the possibility of structure k by preparing maximally entangled state with epsilon error verification. Next, we introduce the importance of self-duality. Here we simply point out the relation between projectivity and pre-duality. In foundation of quantum theory, projectivity is well considered as the postulate of quantum theory. And there are many versions of projectivity in foundation of quantum theory. In this talk, projectivity is the following property. For any pure effect E, there exists a projective measurement, EI, such that an element EI is equal to E. And here, projective measurement means that the post-measurement state of this is given as the normalization of the effect. Projectivity derives pre-duality as follows, where pre-duality means, pre-duality means this inclusion relation. So the dual is generated by pure effects, and there exists a projective measurement. That is a correspondence of effect and the normalized state. Therefore, any element in the dual is included in the original con K, because K is the set of a normalized state. Actually, the present version of of the archive paper is not based on this discussion about the relation between projectivity and plurality. We will revise this. Anyway, in this way, plurality is introduced by projectivity, and self-reality is regarded as saturated situation that state space is restricted and effect space is expanded with preserving projectivity. This is non-trivial statement that plurality can be modified self-reality always. This is shown as a statement later. Now we define epsilon PSES as an entanglement structure with epsilon distinguishability and self-duality. The standard entanglement structure is an example of epsilon PSES for any epsilon larger than 0, but no other simple example is not found. Our question is that, is there any example of epsilon PSES for small epsilon, but for the CES? This is the main question in this study, and the answer is yes. We show that this theorem that is for any positive epsilon, there exists an infinite number of exactly different epsilon PSES. This is the main result. In this way, the possibility of such shared structure cannot be theoretically denied by experimental verification of maximally integral state with tiny errors. Because for any tiny epsilon, there exists integral structure satisfying epsilon undistinguishability. So in order to show this theorem, we give a general theory of self-real cones. First, we obtain the following theorem. For any given plurality cone K, there exists a self-real cone tilde K satisfying this inclusion relation. Simply speaking, a plurality cone can be modified as a self-real cone, this theorem stated. So in this way, repeatability and self-reality is connected by our theorem. Someone might consider this theorem is trivial, but this theorem is not trivial mathematically. Actually, for the proof, we need to apply Solon's lemma, and therefore, this self-real modification is not given constructive form. Due to this weakness, it is difficult to show that two self-real modifications are strictly different, even if plurality cones are strictly different. For example, when we obtain two different plurality cones, but both of their self-real modification might be equal to the CES. In such a case, we cannot show the existence of self-real cone, but for the CES. This problem is resolved by the following theorem. Simply speaking, when we obtain the exact hierarchy of plurality cone, exact hierarchy means such a strict inclusion relation. And then there exist exactly different self-real cones satisfying this inclusion relation. So if we want to show the exactly different existence of infinite many self-real cones, we have to take an exact hierarchy, infinite depth of plurality cones. So due to time constraint, we skip about the idea of the proof, these theorems for a moment. If you want to know this, please ask in question time later. Sorry. Anyway, so then we show the existence of epsilon PSES by main theorem 2. In order to apply main theorem 2, we need to construct an exact hierarchy of plurality cones. In our paper, we construct plurality cone KR with a parameter R. And we can construct KR with satisfying this inclusion relation. So KR is an exact hierarchy of plurality cone. Then, therefore, main theorem 2 implies that the self-real modification tilde KR is exactly different. Also, we need to estimate d of tilde KR. Self-real modification is not given as an constructed constructive form, but the value d of dual KR is larger than any other self-dual modification of KR. And the way of construction of KR enables us to estimate the value of T of dual of KR less than epsilon for sufficiently smaller. Therefore, the self-dual modification satisfies epsilon distinguishability. So, and because epsilon is arbitrary parameter larger than 0, we obtain the following theorem. That is, for any positive epsilon, there exists exactly different infinite epsilon PSES. Here, infiniteness is shown by the arbitrarity of epsilon. Now we give other results. We also show that some example of epsilon PSES has extraordinary performance of perfect state discrimination. Perfect state discrimination is a fundamental task in quantum information theory. In quantum theory, in the standard entangled structure, perfect distinguishability of states is equivalent to orthogonality of states. However, we showed that for some epsilon PSES, there exists a measurement and perfectly distinguishable non-orthogonal states by the measurement. In this way, there exists such shared structure that cannot be denied by verification of maximally entangled state, even if the structure has extraordinary performance for discrimination tasks. On the other hand, we also show that a kind of group symmetry condition this characterizes the sets uniquely. In this paper, we consider such symmetry about a subgroup of general linear group of Hermitian matrices and consider global unitary group defined as this. And as a result, we show that global unitary symmetric entangled structure is uniquely determined as a set. Finally, we simply summarize this talk and give some open problems. In GPTs, there are many possibilities of entangled structures. Especially, we introduce epsilon PSES as an entangled structure with epsilon distinguishability and self-duality. Then we showed that there exists infinite example of epsilon PSES for positive epsilon. This result implies that self-duality is not sufficient for the determination of the sets. Also, we show that some epsilon PSES can discriminate non-orthogonal states perfectly. And this result clarifies that verification of maximally entangled state with errors cannot deny the possibility such a shared structure, even when such shared structure has extraordinary performance for state discrimination, which implies the conjecture that the equivalence of orthogonality and state distinguishability can characterize a set. This is also an important problem. This is an important problem. I'm sorry, we explain. So our proof is just showing the existence of such shared structure. Of course, it is there is a possibility that such a shared structure can be given as a concrete constructive form, but such a construction of epsilon PSES is of a problem. So moreover, we showed that global unitary symmetry characterizes the sets from entangled structures. However, the condition about the global unitary symmetry is quite strong because the aim of GPT is to derive such symmetric structure from operational postulates. Our contribution is to point out that group symmetric condition is essential for the sets. So the reasonable symmetric condition is at most local unitary symmetry, LU. And then it is also an open problem whether LU symmetric PSES exists, but for the sets or not. This is an open problem. That is all. Thank you for your attention.
Thank you, Hayato, for a nice talk. So is there any question?
I would like to have one. Thank you for the talk.
Yes.
My question is, one of these GPTs that are well known is the so-called box world. I'd like to make sure, is it true that there is no entanglement structure there? Or, I mean, in that case, for that GPT?
Yeah.
Or,
In our setting, so instance setting entanglement structure is a model by defined positive con K satisfying this inclusion relation. But standard definition of a box world is not satisfy this inclusion relation. So
sorry, so it is your theory is based on this Hilbert space behind, right? Construction and the usual tensor product. Okay, I see.
But we remark that we emphasize that we define, of course, Hermitian matrices on Hilbert spaces, but we do not assume the structure of positive semi-finite matrices. So this means that we don't assume that vector space as so bracket state.
Okay, thank you. I see. Yeah, thank you very much.
Thank you.
Is there any other question? So I think you focused on the verification of a maximally entangled state. So
yes,
given some theory like epsilon pseudo entanglement structure, is it possible to differentiate that with a standard entanglement structure used in a different state, possibly, rather than a maximally entangled state?
Sorry, do you? So you mean that can we relax the maximally entangled state other than other entangled states? Sorry, what do you mean?
If you consider a different, like different entangled state.
Maybe the assumption of maximal we restrict maximal entangled state is technical reason, but maybe I think I believe that such a realization is possible. So we can consider more general condition, the verification of not maximally entangled states. But this is also open.
Okay, right, thanks. So let's take other questions offline. So let's thank Hayato again for a nice talk.
Thank you very much.